guys, it's ITW, and today we're going to be talking about how we're going to solve the problem of having extra bits relative to the place values of our inputs. Because if you remember, for multiplication and division, we would end up having a few output bits that were actually different, that had different place values as the bits that we were inputting. If they were below it in division, because we needed to include decimals, and they were above it in multiplication, because multiplying two numbers can get you twice as many digits of a result. So yeah, the way that we're going to solve this problem is actually a bit complicated to wrap one's mind around, and basically the really hard part of this series. If you haven't been following along on this point, I suggest you just pause this video and don't watch any further, because it's really just going to get worse and worse and worse from here. So, anyways, first of all, we're going to think about how exactly we're going to solve this problem. So, in all honesty, there really is only one way that we're really going to be able to do that. That is to round our number off. So that's exactly what we're going to do with a floating point number. We're just going to take the three most significant bits, or four most significant bits if you have if you can only store data in 4 bits, and the 4 least significant bits if you divide it. And what you're going to do is you're just going to ignore all the data that comes before it, and just represent it as these guys. But this is fine, and, anyways, the problem with this, though, is how do we know what the least significant bit of this guy is? And there's a really easy way to solve this bit of confusion, and that is to just have one bit that is, one piece of data, which is the actual thing that we've rounded it to, and another piece of data that tells us what the least significant bit of this is, or most significant bit in division. Actually, technically, it's least significant bit for both, or most significant bit for both, if you want to implement it into actual multiplication and division. Anyways, so how exactly should we represent this, though? And the really simple answer is, why not as the number of digits over? And this number right here, I'm just going to say now, is actually an exponent, because we're multiplying this number right here times a certain exponent to get, which is its least significant bit, since we're shifting it over a certain number of bits. So, yeah, but since we're only shifting it over solid bits, then it has to end up being an exponent of 2, just because every single different bit is an exponent of 2. So if we were to shift it over once, then we would be multiplying our value by 2 to the first. If we were to shift it over twice, we would be multiplying our value by 2 to the second, which is 4. And if we were to shift it over 3 times, we would be multiplying our value by 2 to the third, which is 8, etc., etc., etc. So that's basically a little thing that we're going to be using in just a second to actually do multiplication and division with this. Other than that, that's exactly how floating point notation works. You just have your rounded value, and then you're multiplying it by the number of digits of the least significant bit. So, yeah. Now let's get into how we can actually use this in multiplication and division. So let's move on back to arithmetic for a second, and think about what exactly we're doing right here if we're going to multiply these two floating point numbers by each other, or divide two floating point numbers by each other. And first of all, we have to understand that what exactly we're doing here is we're taking our exponent and we are multiplying it by our other value, which is actually called, oh, and I just forgot what it's called. I really am horrible. I always forget what that thing's called, but anyways. So basically, let's look at what that is. it's technically, we're multiplying it by it, right? So that means that we would represent this as this number right here times 2 to the however many bits we shifted over if power. And if you think about it, this is actually very similar to scientific notation. In fact, it's actually binary scientific notation, if you've ever learned that in school. So, yeah. Anyways, so now how on earth is this useful in multiplication and division? And the answer is, since we're multiplying it by each other, we can technically multiply or divide everything in any order that we want. So if we were to multiply two floating point numbers by each other, right, then we could technically just multiply the two values right here, which I am forgetting the name of. I will make sure to put the exact name in the description. I know that there's actually two names. One of them begins with an S and one of them begins with a D. But anyways, so if we multiply these two values or divide these two values by each other, then first of all, we're going to have to put those values back into floating point notation. And then we have a certain number of exponents that we have to multiply by each other, or not multiply, multiply or divide by each other. And if you know anything about exponents, and you've been to school, well, maybe you haven't actually taken this in school yet, then you will know that the way that if you multiply an exponent or divide an exponent by another exponent, then and they're the same base, and the base of the exponent is the exact same thing, which it is since we're multiplying it since these are all powers of 2, then what you do is you just add the exponents together, or you subtract the exponents from the other exponents. So basically what this means is that we can multiply or divide our 2 bits in their 4-bit format, and then all we have to do is add the two values together, or subtract them. And of course, if we had to put it into floating point notation, then we would have to actually add the value that we got in, because we're technically multiplying it by itself. So, yeah, that's basically what floating point notation is and why it's useful. I'm sorry if you were unable to understand this. It really is a really confusing topic. And with that, that just about sums up everything that I wanted to teach at a basic level in this series. However, I will actually be continuing it because you need to implement this stuff into CPUs if it's actually going to be useful. In fact, if you know anything about computer programming, then you will have actually used floating point numbers when you program. Maybe not if you've used Python, but definitely if you've used just about any other language. You will know what a floating point number is. And, yeah. So that's basically all I wanted to go over in this video. And, yeah, see you guys next time.